Okay, so really quickly, if I jump back towards the beginning of the lecture, I wanted to kind of reiterate where we're at, what we're talking about here. Since it's been a week since we've met, we learned the other day that there's 5 processes of respiration and gas exchange occurring in the body. First process is the actual act of breathing, pulmonary ventilation. We talked about that. We talked about number 2, pulmonary gas exchange, which is where we move oxygen from the alveoli into the pulmonary capillaries. CO2 goes in the opposite direction. We skipped 3 and we talked about 4, which is just the inverse of pulmonary gas exchange. Systemic gas exchange is where O2 leaves the blood going into cells and CO2 goes from those cells into the blood. I mentioned we're going to talk about number 5 in its entire own lecture. That'll be what we will get into more so in the last lecture, so hopefully Thursday and into next week. And then number 4 is what we're gonna, or excuse me, number 3, transport of oxygen, carbon dioxide. What we're gonna start with here today. Starting with the transport of oxygen, we've talked a little bit about before. You can see hemoglobin listed here on this page, which we've talked about before. But we'll talk about another way. Let's just read through and we'll go from there. As the gas enters the blood, and it is going to be immediately dissolved in the plasma. Remember, the plasma is the liquid part of our blood. However, fluids are only able to carry relatively small amounts of gases. Therefore, in order for mass transport of the gas to occur, those gas molecules must bind to chemicals in our blood. Thankfully, we have lots and lots of hemoglobin inside of our red blood cells. And that's the way that we carry most of our oxygen. Around 98.5% of the oxygen that we carry in our blood is bound to hemoglobin, whereas in the case of the other 1.5%, that is going to be dissolved in our blood plasma. Only about 1.5% is able to be dissolved in our plasma, and that's because oxygen just doesn't really dissolve very easily in water. And so we're not really going to talk too much about the dissolved form. So we'll talk more about the bound to hemoglobin form. Okay. Oxygen and hemoglobin can bind very easily in a reversible reaction to form what's called oxyhemoglobin, which is just, if you want to think of their relationship like a piggyback ride where an individual jumps on somebody else's back and hitches a ride. Oxygen gets to hitch a ride on the shoulders and on the back of hemoglobin. It's important though to remember that O2 must dissociate or break free from hemoglobin when it reaches our tissues so that oxygen can exit the red blood cell and enter into the tissues. So just like when you get a piggyback ride and you hitch a ride from point A to point B, when you get to your ultimate destination, point B, you were able to hop off, and that's what oxygen has to do to hemoglobin. Now, how much oxygen can be carried by hemoglobin is a pretty well studied thing. Each gram of hemoglobin can unite with 1.34 mils of oxygen. In a standard sample of 100 mils of blood, you're going to find that there's about 15 grams of hemoglobin, and a high percentage of that is saturated in our arteries. So you can take that 15 grams, multiply it by 1.34, because each gram can unite with 1.34, and that tells you if you have a 100 mil sample of blood, you would have roughly 20.1 mils of oxygen, or you could say that it's 20% volume of oxygen. If there's more hemoglobin, maybe instead of 15, we say maybe it's 18 or 20. 18 times 1.34, 20 times 1.34, obviously is going to produce a higher number than this. We don't need to worry about what the number is. So if more hemoglobin is present, more oxygen can be transported in our blood. And the same is true if you reverse it. Instead of 15, maybe we say there's 10 or 12, and whatever that number is multiplied by 1.24 would be less than this. So if there's less hemoglobin, less oxygen that can be carried, more hemoglobin, more. Pretty straightforward stuff. Now the percent saturation of hemoglobin expresses the average saturation of hemoglobin with oxygen. The average oxygen saturation of hemoglobin in our arteries is normally around 97%. In other words, about 97% of our arterial blood's hemoglobin is bound to oxygen. If you've ever been to the doctor and they put that little doodad on your fingertip, that's what they're measuring. Anybody know what that device is called? pulse oximeter, or pulse ox is what a lot of people call it for short, okay? Because they're measuring the oxygen in your blood, okay? It's a pretty cool device, okay? And hopefully when they read it, it's somewhere around that 97%, okay? There are several factors that can determine your percent O2 saturation of hemoglobin by affecting the affinity or the tightness with which hemoglobin binds with oxygen. We want to think of that analogy of, getting a piggyback ride, okay? The tighter you hold on, if you're the one receiving the piggyback ride, okay, the less likely you are to break free and fall off, okay? Or if you're like my kids, when I give them a piggyback ride, whether it's, on my shoulders or on my back, and they like to flail around, and so I have to hold onto the legs. And they have a low affinity, if you want to think of it that way. They're more likely to break free or to dissociate from me, the carrier, like hemoglobin is the carrier for oxygen. The factors that determine this percent O2 saturation include PO2, pressure of oxygen, the temperature of the body, the pH of the body fluids, in other words, blood, and then a chemical called 2,3-bisphosphoglycerate, which is a term that you'll never have to worry about saying or spelling. I usually just call it BPG for short. All right, hemoglobin is going to unload different amounts of oxygen to our tissues throughout the body. In other words, it does not unload the same amount of oxygen to all of our tissues. It's going to adjust and respond to changes in metabolic activity and will unload more oxygen to the tissues that need it the most, i.e. our skeletal muscles when they're performing exercise. Okay, if you want to think of it like this, sitting around listening to me talk, or me sitting around talking, my skeletal muscles aren't really doing much, nor are your skeletal muscles doing much. And we can think back to when we talked about skeletal muscle contraction, all those processes that take place during that process, okay? We know that when muscles contract, they require a lot of energy. They also require a lot of oxygen to get that energy, okay? Well, if the muscles aren't working very hard, they're not needing a lot of energy, so they don't need as much oxygen. So when we're sitting around at rest, it's not necessary to completely flood our skeletal muscles, nor is it completely, or is it important to flood all of our tissues throughout the body with all the oxygen that we can. We only need to dump off what we need to, okay? What we need to get by to match the demands of those cells. The most important factor that determines how much O2 can bind to hemoglobin is the PO2, pressure of oxygen. And I will put a big fat star or highlight that sentence. That's an important thing. If you have an increased pressure of oxygen, PO2 is high, it's going to accelerate hemoglobin association with oxygen, or what we can describe as oxygen loading. So this is like getting on the back of an individual to hitch a ride, okay? Whereas if you have a decreased PO2, it's going to help accelerate oxygen dissociation with hemoglobin, or what we describe as oxygen offloading, okay? Well, we perform oxygen loading where? Where do we load oxygen into the blood and into hemoglobin? Our lungs. Okay? Where do we unload or offload oxygen with hemoglobin? Where do we want that oxygen to break free from hemoglobin? In our systemic tissues, whether that's in our brain, our skeletal muscles, whatever, okay, all those different tissues from the top of our head to the bottom of our feet, okay? Well, since active tissues consume oxygen very rapidly, the PO2 of those fluids is going to remain low, and that's going to help with that dissociation. In fact, there's a really pretty cool, complicated curve that just demonstrates this concept, what we call the oxygen hemoglobin dissociation curve, okay? Notice that when the tissue PO2 is low, and I'm going to show you on the next slide, okay, that hemoglobin will give up oxygen or dissociate it with more easily than when the PO2 is high, which was going to result in hemoglobin binding with large amounts of oxygen and therefore is almost 100% saturated. Here's what the oxyhemoglobin dissociation curve looks like. Okay, it's an S-shaped curve. I actually got two different illustrations showing you the same thing. This one's from your textbook. It's a little more technical. I like this one because it's got a little kind of analogy here. Instead of using a piggyback analogy, they've got a dump truck with stuff loaded in it, or as you can see here and here, the stuff is being unloaded. The dump truck in this analogy is hemoglobin. The stuff that looks like little rocks would be the oxygen. Okay. Now this curve has a very, very steep slope segment to it, but also has kind of a plateau region to it. Okay. Up here at the top at this plateaued region, we would see that what we're measuring here on the y-axis is percent oxygen saturation. So in other words, how much oxygen is bound to hemoglobin. At this top part of the graph, we see the truck is full. Oxygen is bound significantly to hemoglobin. Each hemoglobin can actually bond with 4 oxygen molecules, 1, 2, 3, 4. So this is like one oxygen or one hemoglobin, 4 oxygens. Okay. This is representing what it's like in our lungs, which is what we do in our lungs. We bond that oxygen with hemoglobin as it enters the blood from the alveoli. When we go back to this slide, we said that the PO2 in our alveoli and the PO2 of our blood is pretty high, around 105 in the alveoli, and then in the blood, once that oxygen comes into it, PO2 is around 100 millimeters of mercury. Okay, that high PO2 right here results in almost 100% saturation of hemoglobin with oxygen. Okay, like I just said. Okay, when PO2 is high, hemoglobin will bind with large amounts of oxygen, is 100% saturated. Okay. Whereas this segment of our graph, where we've gone down to a PO2 of 40 or even 20, look what happens to saturation. Okay, especially down here when you get really down on the steep part of the graph. Okay. Well, like I said, at rest, our oxygen consumption doesn't have to be a significant thing. We don't need to unload all the oxygen that we have from our hemoglobin or all the oxygen from our blood. In fact, if you guys are sitting around like this individual here, you're only going to drop off a little bit of oxygen. Okay, remember how I told you guys a few weeks ago that I don't like the term deoxygenated blood? That's because that blood that's coming back to your right atrium right now, when you're at rest, it's still about 75% oxygenated. Okay, that's obviously not completely void of oxygen, is it? Okay, you're still 75% oxygenated. Okay, that's because your tissues don't need that much oxygen because they're not doing that much, especially, for example, your skeletal muscles. Okay, but if you exercise, like this individual is doing here, okay, their tissues are consuming more oxygen, which drops their PO2 from 40 to 20. And even though it's a small change in PO2, it results in a great change in oxygen saturation because it's so steep right here. Okay, and therefore, and this is what we absolutely want when we exercise, we're able to unload more oxygen from the hemoglobin to those working skeletal muscles. Okay. Does that make sense? And that's perfectly what our body needs and wants. Now, there are 2 different ways that this curve can be affected, in ways that it shifts the curve either to the right or to the left. And you're going to want to make sure you put big fat stars and highlight or whatever you need to do to these 2 bottom bullets. Okay. The curve can shift to the right or to the left, which affects the affinity, which we just said affinity is like the tightness in which hemoglobin and oxygen are bound to one another. Okay. If the curve shifts to the right, it lowers or decreases the affinity of oxygen and hemoglobin. So it like loosens the grip that oxygen has on the back of hemoglobin. Okay. And what results is greater oxygen unloading to the tissues. So more oxygen can be released to those tissues, but at the same time, it does limit and result in less loading in the lungs. With regard to a shift in the curve to the left, it does the opposite. It increases or it results in a greater affinity. So oxygen is going to hold on more tightly to hemoglobin, which means it's less likely to be released and less likely to be unloaded to the tissues, and more likely to be or result in a greater loading ability in our lungs. Now, what can cause a shift in the curve? Let's find out. Talk about first what we call the Bohr effect. Not that it's boring, but that it's named after an individual named Bohr, I'm sure. This Bohr effect describes the effect that your blood pH will have on the dissociation of oxyhemoglobin. Any decrease in pH of our blood is going to promote dissociation. So in other words, if your pH drops, it helps break hemoglobin and oxygen connection, that piggyback ride connection. Okay. Well, think about like when we exercise, which we've been using as an example. Especially if you're vigorously exercising, you're going to produce lactic acid and significant amounts of carbon dioxide. Both of those are going to result in pH decreases because as the acidity of our blood increases, remember, that's going to drop your pH because remember, a lower pH is associated with acids. Okay, normal blood pH is 7.4. Okay, but a drop in blood pH, we see here in the red line, has shifted the curve to the right. Okay, and as a result, and this is the big takeaway, this enhances the unloading, which results in a shift of the curve to the right. Okay, so in other words, it promotes, just like we said here, greater oxygen unloading at the tissues, but less loading in the lungs. Okay, if we drew a line from this point here around 100 PO2 came across, we'd only be loaded around 90, whereas normally we're around 95, 97. Okay, whereas if we draw the lines, and they've actually done it for us already, okay, here at the PO2 of 30, we're unloaded down to 38%, whereas here in the black line, if we draw it over, it's about 50%. So we've unloaded more, we've loaded less, but the major takeaway is that we enhanced unloading. Okay, so that's one way to shift it. Okay, now as we produce more carbon dioxide, that PCO2 rises. Okay, and that forms carbonic acid, thus further increasing the acidity in our blood, which promotes more oxygen unloading from hemoglobin. And that's why we also see any higher PCO2 levels in our blood, they also shift the curve to the right. Okay, so to kind of help keep our head straight, let's just write it out. Things that will shift us to the right, shift to the left. Anything that shifts us to the right could be a drop in blood pH, an increase PCO2, and then the reverse is true for shifting us to the left. And that's visible there with the blue lines. Okay, shift left, like what happens if your pH goes up in the blood, means we are more saturated, but we unload less. Same thing happens if our blood PCO2 levels drop. Those aren't the only things that will affect the curve. Two other things that can trigger a shift include temperature changes, and then that chemical I mentioned earlier, 2,3-BPG, or just BPG for short. Okay. Within limits, as temperature increases, so as body temperature goes up, so does the amount of oxygen released from hemoglobin. And if we still think about exercising, not only does our CO2 levels go up, our pH goes down, what happens to our body temperature? It goes up. So exercising would result in higher body temperature. And we see that here, higher temperature around 43 degrees Celsius has shifted the curve to the right. Okay. Heat is a byproduct of all metabolic reactions in cells, and heat produced by active muscle cells tends to raise body temperature. Acids and heat produced by metabolically active cells promotes the release of oxygen from oxyhemoglobin, resulting in a shift of the curve to the right. Okay. Whereas on the other end of the spectrum, if your body temperature drops, like during hypothermia, more oxygen remains bound to hemoglobin, and that's because we don't require as much oxygen because we see a big slowdown in cell metabolism. So we don't have to unload nearly as much. Okay. But if we're just kind of thinking and focusing on exercise, like we've been talking for the last couple of slides, don't we want to unload more oxygen at those working skeletal muscles? Absolutely, we do. Okay. The final thing that can trigger a shift of the curve to the right or to the left is when we have BPG present. Okay. BPG, once again, is short for bisphosphoglycerate, is a substance produced by red blood cells when they go through glycolysis. It will bind to hemoglobin chains as it builds up in the blood, which prevents hemoglobin from binding to oxygen. So it kind of gets in the way. And this therefore decreases the affinity of hemoglobin for oxygen, resulting in a shift to the curve to the right. So when BPG levels are added or elevated, we see a shift in the curve to the right. If we see no BPG or decreased BPG, that might shift it to the left. So if we switch over, add increased body temperature, decreased body temperature, increased BPG, decreased BPG. Now, this is absolutely, I wrote it on here for a reason, something I want you to know for the exam. So make sure you know those different things. I'll ask you questions on the exam. What can shift the curve to the right? What can shift it to the left? Okay. As far as all this information, you're gonna have to walk yourself through the graphs or understand too much specifics. Make sure you know what can shift it to the left, which one can shift it to the right. And then, like I said, put a big fat star, highlight this if you haven't already, what a shift of the curve to the right means, what a shift of the curve to the left means. And it's the bottom sentence that's definitely very important. What it does to loading and unloading. So that's oxygen. Let's talk about how we transport carbon dioxide. Now, in this case, we're driving carbon dioxide from our systemic tissues into the blood, and that's because of the pressure gradient that exists. Once in the blood, carbon dioxide is carried in 3 different forms. We only have 2 different ways to carry oxygen: dissolved and bound to hemoglobin. Well, we actually see the same situation here for carbon dioxide. We see a dissolved form, we see a bound to hemoglobin form, but the majority of our carbon dioxide is in a 3rd form, bicarbonate. And I'll talk about that here in a second. Okay. Let's first talk about the dissolved form. Only about 7 to 10% of carbon dioxide is carried in this form, which is actually significantly higher than the 1.5% of oxygen. Okay. If you did not know this, I'll tell you it anyway. When you drink something that's carbonated, like the Dr. Pepper that I have sitting in front of me right now, or LaCroix, or anything else that, you pop it, or you open the tab, it fizzes. Guess what that fizz is? Carbon dioxide. That's why they call it carbonated. Okay. Those liquids, when sealed, like the Dr. Pepper in front of me, have the dissolved carbon dioxide in them. And then when you break that seal, those bubbles are the carbon dioxide going from the dissolved form into the liquid or to the gaseous form. And that's why if you like let the Dr. Pepper sit on the table with its lid off for a day or two, it gets flat. All that carbonation is gone. So our blood can have some dissolved carbon dioxide in it. Okay. We've learned this before, but our blood can, or our hemoglobin, I should say, can carry carbon dioxide. Only about 20% of the CO2 is carried in this form in what we call carbaminohemoglobin, and significantly less than a 98.5% of the oxygen that we carry bound to hemoglobin. That leaves us with 70% of the carbon dioxide carried in the form of what we call bicarbonate ions. Okay, and this is going to be what is formed when we hydrate water, or when we hydrate CO2. Hydrate just means to combine with water, which we've talked about this before, but now we get to see what's actually taking place. As that CO2 combines with water, it forms an acid called carbonic acid. That's what this is, H2CO3. But then that carbonic acid dissociates or breaks apart into hydrogen ions and HCO3, which is what bicarbonate ions are. This is possible, and that is because of, and we've talked about this enzyme before, carbonic anhydrase, which is found in our red blood cells. Okay. This enzyme can take carbon dioxide and form water and go in that direction to result in eventually the formation of bicarbonate and hydrogen ions. But this enzyme also is what catalyzes the reaction that takes the reaction and goes in the opposite direction from the hydrogen ions to the bicarbonate to the acid, and then eventually the CO2 and the water. So it's an enzyme that catalyzes the reaction in both directions. So we could say that's a reversible reaction. Okay? And that's why we see these double arrows throughout the chemical reaction right here. Now, what happens to the hydrogen ion? What happens to the bicarbonate? Some of the hydrogen ions can bind to hemoglobin. The rest diffuse out of the red blood cells into the plasma. Okay, that's important because, as we've talked about before, if CO2 builds up in our blood, what happens to our body? It becomes acidic. Okay? Remember, hydrogen ions are always associated with acids. Okay? And since hydrogen ion is a product of the dissociation of carbon dioxide, as CO2 increases, so does the concentration of hydrogen ions in our blood, which results in a drop in pH. Okay? And in just a couple of slides, we're going to talk about how this drop in pH will stimulate what we call the carotid bodies, which triggers increases in ventilation to rid more CO2, which thus helps us decrease the amount of hydrogen ions in our blood. Okay? So we'll talk about how this reaction is going to affect our ventilation, our breathing. Okay. When I say increased ventilation, I'm talking about increased breathing rate and increased depth of breathing, breathing in more rapidly and more deeply. Okay. As the bicarbonate is formed, okay, a lot of that diffuses out of the red blood cells, which creates an electrical gradient that is established for chloride to diffuse into the red blood cells. And we call this exchange a chloride shift. I'll point that out on the next slide. Okay. And then as that blood passes through the pulmonary capillaries and lungs, all these reactions are reversed. So let's walk through it. We'll actually start down with the bottom figure. And we're going to focus on CO2, which is formed in our tissue cells. Then comes out into the interstitial space, then crosses into the blood, like we show right here. Some of that carbon dioxide is just going to be circulating in the plasma as the dissolved state. Most of it goes into our red blood cells, where it either combines with hemoglobin, like we show right here. This is HbOC2, which is carbaminohemoglobin. But most of that CO2 is combined with water and goes to that reaction we just talked about, resulting in the formation of bicarbonate, which goes back out into the blood, and the hydrogen ions that will either bind to oxygen or bind to hemoglobin, or it doesn't show it, but will go out into the plasma as well. Okay. Now, while bicarbonate comes out of the red blood cell, chloride comes in. That's why we call it a chloride shift. Once we get to the lungs and we want to get that CO2 out into the atmosphere by breathing it out, we just reverse everything. So here we take that hydrogen ion that was bound to hemoglobin. We take those bicarbonate ions back into the red blood cell. Now the chloride comes out, so we have a reverse chloride shift. The hydrogen ions and the bicarb join back together, forming H2CO3, carbonic acid, which then dissociates this time to form CO2 and water. The CO2 then leaves the red blood cell, eventually enters the alveoli. The CO2 that's in our plasma can go out into the alveoli, and the CO2 that's bound to hemoglobin breaks free and then is going to follow the same path that the CO2 that was formed. So that's what's taking place. We just do this down here, and then we do the exact opposite of it up here. With regards to oxygen, most of that oxygen, as we know, binds itself to hemoglobin, forming oxyhemoglobin. And then when we get to our tissues and that oxygen needs to dissociate, it breaks free and then enters our tissues like so. It doesn't show the oxygen that's out in the plasma, but that's once again only about 1.5%. About 98.5% is bound to hemoglobin. Okay, so that's how we transport oxygen and carbon dioxide. Okay. Let's now talk about how we control ventilation, how we control our breathing rate and depth. The homeostasis of our blood gases is maintained primarily by changes in our ventilation. Okay, the rate, so how fast and how deeply we breathe. Okay. The three basic elements of our respiratory control system make a simple feedback loop, which I've kind of created my own here. We've got, just like any other feedback loop, the three components are sensors or receptors, which detect changes to the body. In this case, they're going to detect changes to our blood chemical concentrations. They send information, input information to our respiratory control centers. Guess where those are going to be at? Where are most control centers? In the brain. We've actually talked about these before. It's going to be in the pons and the medulla. They then send out output signals to the effectors, which are going to be our respiratory muscles like the diaphragm and the intercostal muscles that we talked about, which cause them to contract more or less, depending on what's going on. And that either is going to make us breathe more rapidly, more deeply, or less rapidly and less deeply. So let's talk about it. We're not going to get into too much about the effectors, those muscles, because we've already done that. We talked about breathing last week, right? Talked about the diaphragm, how it contracts to allow us to breathe in. But we haven't talked about the control centers or the sensors, at least not in this lecture directly. Okay. Our respiratory control centers, there's 4 major ones, although the first 3 are the kind of true major ones. Your medullary respiratory or rhythmicity center is something that we learned about previously. It's in the reticular formation of the medulla, hence the name medullary. And this is the control center most responsible for our basic rhythm of ventilation. So it helps set our breathing rate. Okay. The apneustic and pneumotaxic areas or centers are in the pons. Okay. The apneustic is in the lower pons, not that that's really important, but is the center that sends stimulatory impulses to the medullary rhythmicity center and results in activating and prolonging in inhalation, which as a result, we have a more long and deep inhale. So that's what the apneustic center does. Pneumotaxic center, which is in the upper pons, helps turn off the expiratory area before our lungs become too full of air. And thus, when it is more active, our breathing rate is more rapid. These 3 are responsible for subconscious breathing, which is breathing like 99% of the time when we're not thinking about it and it's just being done automatically for us. But I can tell you guys all right now, and you can do it, unlike what we can do to like our heart. You can't tell your heart to stop beating, can you? Can you tell your body to stop breathing? Absolutely we can. To a certain degree.
Right.
Everybody hold your breath. You can do it, right? Breathe more rapidly. We have conscious control within limits, thanks to our cerebral cortex. So breathing is generally under voluntary control to a considerable extent. The cortex can override the function of the brainstem within limits. Within limits. We can't hold our breath forever. Obviously, we'll die. Okay? But we won't actually die. And this is like little kids that threaten to hold their breath. If worse comes to worse, they'll pass out, and then they'll just start breathing normally anyway. Okay? It's scary as a parent. Thankfully, my kids haven't done that though. Now, why would we ever want to voluntarily control our breathing? Or think of it this way, why would we ever want to stop breathing? Every time we take a shower, every time we jump in a pool, anytime you're in a car and somebody lets one rip, okay? You can hold your breath to prevent water or irritating gases from entering the lungs. But once again, this is all within limits. So this ability to not breathe, however, is limited by the buildup of carbon dioxide and hydrogen ions in the body. And as those levels build up in the body, they're going to trigger these chemoreceptors. We have two types of sensors, central and peripheral. The central chemoreceptors are located up in the brain near the medulla, surrounded by brain extracellular fluid, and that's what they're monitoring, the concentration of hydrogen ions in that extracellular fluid. Any increase in hydrogen ion concentration stimulates ventilation. So in other words, if hydrogen ion levels go up, we're gonna breathe more rapidly. Okay. Any decrease hydrogen ion concentration inhibits ventilation, so we breathe less rapidly. Okay. Your peripheral chemoreceptors are going to be the same receptors that we talked about back when we talked about blood pressure. They're located in the carotid bodies at the bifurcation of the common carotid arteries and the aortic arteries, aortic bodies above and below the aortic arch. So basically your upper chest into your neck. Okay. They respond to three things, and it's the same three things that we talked about in our blood vessels lecture when we talked about blood pressure. They respond to decreases in arterial PO2 or decreases in pH or increases in arterial PCO2. Any one of those three things triggers these guys. Now, if I told you guys to hold your breath, all three of those things are going to happen. Because if you're not breathing in, what happens to your arterial PO2? You're not breathing in oxygen, PO2 in our blood is going to go down, right? Okay. If you're not blowing out CO2, that PCO2 of our blood will go up. And as we just learned, anytime CO2 levels go up, so does the production of hydrogen ions, which results in drops in pH. Okay, so just holding your breath triggers all three of these same things. And as a result of increased PCO2, decreased pH, or decreased PO2, both the central and peripheral chemoreceptors will stimulate the inspiratory center, which will cause hyperventilation. What's hyperventilation? It's like what you hear about when somebody's hyperventilating, they're like breathing really rapidly, or it's just an increased breathing rate. Okay. This allows increased oxygen inhalation, more CO2 exhalation. Okay. And that's what we're showing here with this feedback loop. We have some type of stimulus, doesn't really matter what it is, disrupts homeostasis by causing arterial PCO2 to increase, or by decreasing pH or PO2. Triggers both the central and the peripheral chemoreceptors, which result in input to the brain, especially the medulla, which triggers output signals that go to our breathing muscles, the diaphragm, the intercostals. We breathe more rapidly, which helps us blow off the CO2, breathe in more O2, and helps elevate our pH. And not always a negative feedback to where we're opposing that change and hopefully going back to normal. Now, there's several other mechanisms that can regulate respiration. And those are listed here on this page. Okay. We can alter our breathing rate using information coming from our proprioceptors. You don't remember, proprioceptors are the receptors in places like your muscles, your tendons, and your joints. Okay. Well, why would those be providing information to your brain to adjust breathing? Well, if you think of it this way, if I asked you guys, okay, all of us, let's get up and go outside. And whether you're there in Wamego or here in Atchison, I told you guys to go stand in the road and sit there for a second. And then as soon as I say go, I want you to take off sprinting as fast as you can. You're going to go from resting conditions to, if you're running as fast as you can, maximal exercise in an instant. Okay. Do you think at that quick amount of time, the first few seconds, you're going to see much change to your blood's pH, PCO2 or PO2? No, but your muscles are needing oxygen delivery almost instantly. Okay. As soon as they start pumping like they are, they need more oxygen, they're producing more CO2. That's why these guys become active, so that we increase our rate and depth of breathing even before changes in hydrogen, PCO2 or PO2 occur. Does that make sense? Okay. The inflation reflex involves stress-sensitive receptors called baroreceptors, which are like the ones that we learned about in our blood vessels lecture, except these are in the walls of our bronchi and bronchioles, our airways, our air tubes in the lungs. When they are overstretched, when we overinflate the lungs, they send nerve impulses are sent along the vagus nerves to the inspiratory and apneic areas in the brain. And as a result, these brain regions are inhibited, which causes you to exhale. Okay, this exhalation reduces the stretch on them and the stimulus is stopped. So it actually kind of works in a fairly similar manner to the baroreceptor reflex that we talked about with blood pressure. What's your limbic system? Your emotional brain. And we've talked about things like how anxiety and emotions can affect your blood pressure, your heart rate, right? What about your breathing rate? Absolutely, they can. Okay. Anticipation of activity, emotional anxiety may stimulate the limbic system, send signals that increase the rate and depth of ventilation. In fact, you see it in movies and TV shows all the time. Somebody's all nervous and worked up. They might start literally hyperventilating, right? And then you see them like the old meme where they're breathing into the mask to settle them down. That actually does help. Okay. But that's an example of a completely emotional, mental thing and how that can affect a visceral response. Okay. Body temperature. Any increase in body temperature increases your rate of inspiration. So if you're more heated up, you're going to breathe more rapidly, whereas a decrease in body temperature is going to decrease your rate of inspiration. If you were to jump into a cold pool or accidentally turn the cold knob on the shower, that'll actually take your breath away. That'll cause a temporary apnea. So will pain. Sudden severe pain causes apnea, whereas a prolonged pain increases your respiratory rate. I have no idea how somebody figured this out, but stretching the anal sphincter muscle actually increases the respiratory rate. I don't know why somebody would have figured that one out, but that's actually something that I was reading that like paramedics sometimes utilize. It sounds really weird, but like if a baby's not breathing or they're breathing really slow or not very deeply, they can make the baby breathe more rapidly by putting the finger up their beehole. Okay. Desperate measures call for whatever that saying is, you know what I'm saying. Okay. Irritation of the airways can cause immediate cessation of breathing, followed by coughing or sneezing. And then blood pressure changes. Any sudden elevation of blood pressure decreases your respiratory rate, whereas any drop in blood pressure increases it. All right, last thing I want to do is just really briefly talk about oxygen consumption. So we've talked a lot about PO2. Well, now we see the abbreviation VO2. VO2 is short for volume of oxygen, or how much oxygen. Okay. Oxygen consumption, which is abbreviated VO2, is the amount of oxygen consumed by the tissues of our body. Okay. As our body performs more work, the demand for more energy increases, which thus results in an increased amount of oxygen that we must extract from our blood, because aerobic respiration increases oxygen extraction. Okay. Well, if we look here on the next page, we have a graph that demonstrates this very linear relationship between work rate, or basically exercise intensity, and your VO2. Okay. We look here, work rates are measured in watts. In other words, basically, if you look at 0 here, this is resting conditions. Over here at 300, this would be extreme high intensity exercise. Okay. Running fast, cycling fast, swimming fast, whatever it is. Okay. Well, probably makes pretty good sense. The harder you work out, the more oxygen you consume. And it's a very straight linear relationship. In fact, for every increase in 1 watt, we're going to increase our oxygen consumption by about 10 mils per minute. Okay. Notice that the line doesn't start at 0. Okay. That's because at rest, we're still consuming some oxygen, right? About 1/4 liter per minute we're consuming at rest. Okay. And that is going to go up very linearly until the point where it plateaus off, which is the point where we cannot consume any more oxygen. And we call this point our VO2 max, which is the maximum of oxygen consumed by the tissues of the body. It is something that you can absolutely train to increase, but the most influential determinant on your VO2 max is your genetics. Okay. If you want to understand the importance of VO2 max, think of it as the best predictor of your ability to exercise for long periods of time. In other words, to perform endurance type activities. So if you want to be a really good marathoner, if you want to be a really good cross-country skier, actually those athletes have the highest VO2 max. Cyclists like Lance Armstrong that you've probably heard of before, not sprinters, but long distance athletes have high VO2 maxes. If you want to be a high level Olympic type athlete, running marathons, or like that video I showed you a few weeks ago with the ladies doing the Ironman, the best way to become an Olympic athlete, if you're not already one, is to pick your parents wisely. What I'm saying is it's genetics, that's the primary determinant. And I've included a table here to kind of give you some values. Like I said, cross-country skiers typically have the highest. Okay, distance runners are not too far behind. You can see what happens if you're sedentary. Okay, almost half or even less than half of what a cross-country skier would have. People with diseased lungs, very low VO2 max values. Thus, those people are going to have a hard time just walking up and down their stairs to the bathroom. My neighbor has COPD. He can barely move around his yard, so I have to help him do a lot of different things. And we kind of talked about some of that stuff the other day. Not going to ask you anything, values or anything like that. Do understand what VO2 is short for, the amount of oxygen consumed by the tissues, and know what VO2 max is. Sound good? Any questions? Okay. With that said, we are finally done with our respiratory system. Feels like it took us forever. It's a big lecture, a lot going on. As is our next lecture.